Every organic reaction is driven by a single physical imperative. Electrons flow from high-density sources to low-density sinks. We typically model this flow as a sequence where a substrate and a reagent combine to form a temporary intermediate, which then resolves into a final product. This sequence often begins with a process called heterolytic bond cleavage. As shown in this document, the bond breaks asymmetrically, pushing shared electrons onto one fragment and creating distinct ions. Looking at the center, the carbon atom forms a carbocation. It assumes a trigonal planar geometry, defined by an empty, unhybridized p orbital. A common heuristic in chemistry is to look for the highest formal negative charge to identify the most reactive participant. But a high negative charge does not automatically equate to high chemical reactivity. Relying purely on formal charge overlooks the physical reality of a reaction. To determine how a molecule will actually behave, we have to look at kinetics and thermodynamics as separate factors. We define basicity as a strictly thermodynamic, equilibrium-driven process. It specifically measures a molecule's ability to abstract a proton. When an electron-rich species acts as a base, it attacks an electrophilic hydrogen atom. This extraction typically forces the molecule to undergo an elimination reaction, forming a new double bond. Nucleophilicity is a kinetic measure. It dictates the rate at which an electron pair is donated, specifically to an electrophilic carbon atom, resulting in a direct substitution and a new carbon bond. The physical site of the attack dictates the entire chemical outcome. Target the proton, and the molecule is a base. Target the carbon, and it is a nucleophile. Because attacking a carbon atom requires navigating past other attached groups, factors like steric hindrance play a massive role. A bulky, highly charged molecule might be a strong base, but its physical size prevents it from being an effective nucleophile. To predict whether substitution or elimination will dominate, we must abandon simple charge arithmetic and examine how the physical molecular orbitals overlap in three-dimensional space. This leads us to frontier molecular orbital theory, or FMO, which focuses on the specific energy levels of the outermost electrons. This chart maps the two critical energy boundaries in any reaction. The nucleophile acts through its highest occupied molecular orbital, the HOMO, while the electrophile receives electrons in its lowest unoccupied molecular orbital, the LUMO. As depicted in this orbital mixing diagram, a reaction is favored almost exclusively when these two specific frontier orbitals interact with each other. When two non-orthogonal atomic orbitals overlap, they mix to generate two entirely new molecular orbitals, one higher in energy and one lower. The defining rule of FMO theory is that the maximum stabilization energy is achieved only when the interacting HOMO and LUMO are very close to each other in initial energy. The energy gained from this specific frontier interaction must be substantial. It has to overcome the energy penalty incurred when the other fully occupied orbitals within the molecules clash and mix. The geometry of the approach matters just as much as the energy. The physical degree of overlap dictates the mixing efficiency, which is why a direct head-on sigma bond overlap is inherently stronger than a parallel pi bond overlap. Electric charge tunes these energy levels. On the right, a negative charge raises the methyl anion's HOMO energy, increasing nucleophilicity. Conversely, on the left, electron withdrawing groups drop the LUMO's energy level, creating a highly receptive target. Synthesis ultimately relies on the meticulous tuning and matching of these orbital energy heights to force a specific chemical reaction. These orbital matching mechanics map directly onto Ralph Pearson's hard and soft acids and bases theory. In the HSAB framework, we classify hard species by tight, rigid electron clouds, small atomic radii, high charge states, and weak polarizability. Soft species represent the inverse. They have large radii, low charge states, and highly diffuse, strongly polarizable electron clouds. The foundational maxim of HSAB is that hard acids bind strongly to hard bases, and soft acids bind strongly to soft bases. We can apply these parameters across the three distinct classes of nucleophiles. Looking at this SN2 mechanism, lone pair nucleophiles use unshared electron pairs to make a new bond, which increases their formal charge. Sigma bond nucleophiles operate differently. As outlined in this section, they utilize the electrons within an element-metal bond. During the reaction, the formal charge of the nucleophilic atom itself does not change. Instead, the metal's charge increases by 1. The ultimate predictive test for HSND theory is its application to ambident nucleophiles, molecules equipped with multiple potential attack sites of varying hardness. In 1954, Nathan Kornblum formalized a rule for these complex molecules. In an SN1 reaction, the intermediate is a carbocation, a hard acid. Therefore, it will preferentially react with the most electronegative, hard base site on the nucleophile. In an SN2 reaction, the target is a tetravalent carbon, which behaves as a soft acid. It will bypass the hard site entirely and react exclusively with the soft base site. By categorizing molecules into hard and soft orbital profiles, chemists can accurately predict regiochemistry, pinpointing exactly where a bond will form even when multiple targets exist. To see the limits of these rules, we look to the extremes of organometallic chemistry, specifically transition metal carbonyl anions. These metallic complexes are classified as supernucleophiles. They are defined by an extreme supersoftness and a massive reducing power. Their central anomaly is that they easily and spontaneously react with completely unactivated aryl and vinyl halides. These unactivated substrates are highly stable. Historically, they are entirely inert to attack from standard highly electronegative nucleophiles. Supernucleophiles reverse standard leaving group efficacy. Instead of the typical preference for strongly electronegative fluorine atoms, they preferentially react with massive, soft iodine atoms. We can explicitly rule out standard kinetic mechanisms. These reactions do not proceed through the classical addition-elimination route, nor do they rely on single electron transfer pathways. When extreme supersoftness meets an unactivated substrate, the classical kinetic models simply fail. We need a different mechanistic framework to explain the reaction. The reaction proceeds through halogen-metal exchange, or HME. First, the super-soft metal anion completely ignores the carbon atom. Instead, it directly attacks the halogen, stripping it away to leave an intermediate carbanion. This carbanion is highly unstable. It rapidly collapses, yielding the final nucleophilic substitution product. Chemists verified this unusual mechanism through a process called anion trapping, utilizing a strong proton donor like tert-butanol. If the intermediate carbanion exists, the tert-butanol will intercept it before it can collapse. Experiments proved exactly that. The alcohol protonates the carbanion, entirely suppressing the expected substitution and leaving a dehalogenated product instead. Further physical proof was isolated during experiments with specific rhenium and manganese supernucleophiles. Here, researchers recovered structurally intact halo-acyl metallate anions. These stable complexes physically imprint the intermediate steps of the halogen-metal exchange into their final molecular structure. True chemical reactivity is determined by dynamic orbital alignment. By mapping the quantum profiles of reagents, their energy heights, hardness, and spatial overlap, chemists can execute reactions classical rules deem impossible.